Hello everyone, this is Chandra Sir welcoming you all to this wonderful Ground Zero series. As you all know, in this series we bring the most important concept and try to make it simple, easier and interesting for you to understand through animation. So in today's session, I will be going to discuss about one of the most important concept of the subject heat transfer, that is critical insulation. How the insulation method can affect the rate of heat transfer. Before I start my session, let me quickly introduce myself. I am mechanical engineering graduate from IIT Delhi, having more than 10 years of teaching experience in GATE, IES and PSUs. Also, I have cleared engineering services examination and worked in Steel Authority of India Limited for a couple of years. You can connect with me through the mail ID which is there on the top of the screen, and you can join me on the Telegram as well, that is Mechanical by Chandra Sir. The link is also there on the bottom of this screen. So let us start our discussion. We will first of all try to find out the effect of insulation on a plain wall system. All right. So first of all, let us try to understand without insulation how the heat transfer rate will be. If there is a plain wall having the surface temperature as Ts, it is in contact with the fluid which is at the temperature T infinity. So there is a convection from the surface of the bare wall to the fluid or the ambient. So the mode of heat transfer will be convection. If we draw the circuit diagram or thermal circuit diagram, then there will be a single thermal resistance, that is convective resistance, and the expression will be 1 upon H into A. That is the convective resistance, and Q will be equal to delta T. Delta T is the temperature difference between the surface and the free stream temperature of the fluid upon 1 upon HA. That is the rate of heat transfer without any insulation for bare wall. Now, if we insulate the surface of the plain wall with some insulating material, then what will happen? The surface temperature of the bare wall is still Ts, fluid temperature is still T infinity, Ts is more than T infinity. But because of the insulation, there will be conduction. The thickness of insulation is, let us say, X. There will be conduction first from the bare wall to the insulating material, and then the same heat will be transferred to the fluid through convection. So there will be two thermal resistances which will be in series. For conduction, the thermal resistance is X by Ka, and for convection it will be 1 upon Ha. So the equivalent thermal resistance will be equal to R1, that is conductive thermal resistance in the insulating material, and plus R2, that is the convective thermal resistance for the fluid. So as you can see, if we increase the value of X, if we increase the thickness of insulation X, then what will happen? There is an increase in the conductive heat transfer resistance, thermal resistance for conduction, and that will increase. There is no effect on convective thermal resistance. So the equivalent thermal resistance will increase, and Q is inversely proportional to equivalent thermal resistance. So by increasing the equivalent thermal resistance, there is always a decrease in the rate of heat transfer. The maximum heat transfer rate is for a bare wall when X is equal to 0. As we increase X, the value of Q will keep on decreasing. So we have observed that in case of a plain wall, if we insulate the surface of the plain wall with some insulating material, there will always be a reduction in the rate of heat transfer. But what happens to the radial system, like a cylinder or a sphere? When the outer surface of the radial system is insulated, we will try to find out the effect on the rate of heat transfer. But before that, we need to understand first that without insulation, what is going to happen or how the heat transfer rate will take place. So there is a radial system. The surface temperature is again Ts. It is in contact with the outside fluid having a temperature T infinity, and the area of the radial system without insulation is A naught, outer surface area which is in contact with the fluid. So there will be convection if Ts is greater than T infinity. The mode of heat transfer will be convection, and if we draw the circuit diagram, it will be a convective thermal resistance, which will be equal to 1 upon H into A naught. Right? This is delta T, that is Ts minus T infinity. So Q without insulation is equal to delta T upon 1 upon H into A naught. Right? Now, if we insulate the outer surface of the radial system, what is going to happen? Let us try to find it out. If we insulate, then the area, outer area will become A. Earlier it was A naught. Because of insulation, there is a radial thickness gets increased. This is the radial thickness LR. So in the insulating material, initially the mode of heat transfer will be conduction, and then the same heat will be convected through the outside fluid. So if we draw the circuit diagram, then our circuit diagram will have two thermal resistances, one for conduction in the insulating material, another is for convection in the outside fluid. So they will be in series. So R1 can be written as R1 is R conduction, that is for conduction in the insulating material, and that will be decided by the thickness of insulation, which is called as radial thickness. So what we can say, conductive thermal resistance is directly proportional to radial thickness of insulation LR, and convective thermal resistance, that is 1 upon HA, it is inversely proportional to outside area after insulation. R convection is proportional to 1 by A. Area is getting changed due to insulating the radial system, and the radial thickness is also getting changed. So both are getting affected due to insulation of a radial system. Now, if we increase the radius of insulation, if we make the insulation thick and thick, then what will happen? By increasing the radius of insulation, the radial thickness of insulation will increase, LR, and that will increase the conductive thermal resistance of the insulating material. And at the same time, by increasing the radius of insulation, the outer surface area of the radial system will also increase, and that will reduce the convective thermal resistance of the radial system. Because the area is increased, so convection thermal resistance will decrease, because R convection is inversely proportional to area. So what we can see from here is the equivalent thermal resistance, which is R1 plus R2, can increase or can decrease, and Q is inversely proportional to R equivalent. So Q can decrease or can increase. So there is a possibility in case of radial system that by increasing the insulation, by applying the insulation, there is a chances of increasing the rate of heat transfer. All right. So if we see the radial system, initially when we apply the insulation, for some amount of insulation, for some thickness of insulation, the convection dominates. The increase in outer area will be having more effect compared to the increase in radial thickness. So the convection parameter, or the convection heat transfer rate, or the convection thermal resistance will have more dominating effect. So by increasing the radius of insulation, we will only focus on the convection. Convective thermal resistance will decrease because of increase in area, and that will decrease the equivalent thermal resistance. And we can say Q after insulation will increase because Q is inversely proportional to equivalent resistance. That is up to some thickness. After this critical thickness, we call it as critical thickness. After this critical thickness, the conduction term start dominating. The effect of radial thickness will be more dominating rather than the effect of increasing the outer area due to increasing the insulation. So we will focus on the conduction now. By further increasing the radius of insulation, what is going to happen is the conductive thermal resistance will also increase because it is directly proportional to LR, and that will increase the equivalent thermal resistance, and we can say the Q with insulation will start decreasing. So what we have observed here is initially up to some thickness the heat transfer rate is increasing, and then it will start decreasing. So we can find out that critical radius of insulation. So this is, if I show you it through graph, this is R equivalent. Then by increasing the radius of insulation, let me change the color here. By changing, this is R equivalent. So this is R is equal to R naught without insulation. As we increase the radius of insulation, there is a point coming that is called as critical radius of insulation. Initially, the equivalent resistance will decrease because convection dominates. Here convection dominates, and it will be minimum value. It will attain the minimum value, and then it will start increasing because conduction will start dominating. If we draw the curve for the rate of heat transfer without insulation, the heat transfer rate is this. This is corresponding to R naught. This is, it will increase the rate of heat transfer. It will become maximum at some point. That corresponding radius of the system is called as critical radius of insulation, and then it will start decreasing. So we can easily find out the critical radius of insulation for a radial system, corresponding to which the equivalent thermal resistance is minimum, or corresponding to which the heat transfer rate is maximum. So if we talk about a cylindrical system, so the condition is, if we want to find out the condition of attaining the critical radius of insulation, we can say equivalent resistance should be minimum, R equivalent should be minimum, then only the rate of heat transfer will be maximum. So if we find out the differentiation of R equivalent with respect to R, then we can find out the value of RCR. Critical radius of insulation for a cylindrical system will be K by H, where K is the thermal conductivity of the insulating material and H is the convective heat transfer coefficient of the outside fluid which is in contact with the insulating material. Similarly, for a spherical system, if we do the if we differentiate the equivalent resistance with respect to R and put it as 0, then we will obtain the critical radius of insulation for a spherical system as twice of critical radius of insulation for a cylindrical system. That is the point where the rate of heat transfer will be maximum in case of radial system, and if we increase the insulation further, the rate of heat transfer will start decreasing. So that is all from my side in this session. I hope you have liked it and you have understood the basic concept of insulation to increase or to decrease the rate of heat transfer. Thank you guys. Thank you for joining in. See you in the next such video. Thanks a lot.